Okay, so here we have the simulation of firing some light at an hydrogen atom. All right, so here we've got our torch or our light ray gun thing. All right, and we've got all sorts of different wavelengths of light. All right, that's what happens in white light. We've got all these different wavelengths, so different colors. Okay, and the kind of purpley ones that look a bit like stars are our UV light. So they're not visible to the human eye, but they're still present wavelengths, and that wavelength tells us sort of how much energy each bit of light has. Okay, so what this bit down the bottom is showing us is how many photons, so how many packages of light are being released from the atom per different wavelength. So we've got lots being released down in our UV section, and we've had one in our range of our blue light. All right, so what we can see from this experiment, what really happens is specific wavelengths of light are being absorbed into our atom, whatever it looks like, and then some bits of light are being released. Okay, so if we turn to our predictions, we start with our billiard ball model. Okay, and this says that the atom is the smallest thing, there's nothing smaller than it, it's a solid sphere. So if we shot light at our atom and we saw this, the billiard ball model would have been correct. All right, so in this case we've got all wavelengths of light bouncing off our atom. Okay, and as you saw before, that's not the case. So let's see, we've now discovered the electron, and we know that the atom is overall neutrally charged. It has no charge either way. So we've got this red sort of cloud of positive charge, all right, which our electron sits in. And there's only one because we're talking about a hydrogen atom here. Okay, and this model is saying that any light wave can be absorbed, so any color can be absorbed, all right, but it's always going to release, see down the bottom here, it's always going to release the same wavelength of light. And that's not too important, we look more at that next year, but just so you know what's going on down here. So again, this is not what we saw before, because in our experiment, if we go back, if we watch what's going through here, anything that is coloured, okay, so is not in the UV range, does not get absorbed. Okay, but if we go back to our plum pudding model, as long as anything hits the electron, any wavelength, that gets absorbed. So that's not quite right either, that's not quite what we saw. All right, then we have a look at the classical solar system, which is Rutherford's, and we've got to look really quick because our electron gets attracted by the positive charge of the proton and kind of gets sucked into the nucleus, and then that's our atom over. Okay, and we know that's not the case because we wouldn't exist if that was happening. Okay, so if we have a look at this again, we had a high electron energy level to start with, and as it spiraled in, it dropped to nothing, and we can't get that back. We've lost our atom. All right, we know that definitely isn't the case, so we must have a better model. Okay, and this is Bohr's model. You would have seen this in year 10 perhaps. This is where we start getting that idea of energy cells, valence electrons, all of that kind of thing. So what you should be noticing here is we've got our one proton in the middle, nice and handy, and we've got our electron around the outside. And it usually hangs out in that very inner electron shell. But what you'll notice is when it gets hit by a specific wavelength or a specific couple of wavelengths, in this case it's in the UV range, the electron jumps out further. And on this side, on the electron level, we'll notice that it jumps up the levels, right? So out further away from the proton. And then what happens is as it drops back down those levels, it releases different amounts of energy depending on how much it drops down by. So how much it jumps up by depends on the wavelength of light that it absorbs, and then how much it drops down by determines the colour or wavelength of light that it emits as it drops back down those energy levels. Now this explains quite a lot about an atom, and it's still a really good model to use. Alright, but here we've got this sort of discrete, nice little package of negative charge as our electron. Okay, but we know that's not actually the case. So what we have here is we have a more quantum view of electrons and the atom. So instead of having one nice little package of negative charge as our electron, we have this area, this band. Okay, and if we have a look at it from sort of 3D, we'll notice that it's wiggling. So what that's doing is it's saying that this is the movement of our electron or our charge. So instead of going around, sort of orbiting our nucleus like a sort of planet system, all right, we have these areas of these energies. Okay, and that's because we've worked out that we can either know the location of the charge, or we can know the size of the charge, but we cannot know both at the same time. Okay, so this is to get more into that side of our atom. And then we have Schrodinger's atom. So this is this clouds of energy. So you'll see this more in chemistry. Talks about it, looks at it more in this way. All right. And again, we have those specific wavelengths of UV light that are getting absorbed. And what they're doing is they're shifting where some of that negative charge is in relation to our proton, our nucleus. Okay, so the models that we're really concerned with are our billiard ball, vastly incorrect. Our plum pudding, well, it's starting to get there, we've at least got an electron. Our solar system, which has got the bits in the right place but can't explain why they stay there. And then Bohr's model. Those are our four most important ones. All right, so for this part, we don't really need to look at de Broglie's and Schrodinger's as models, but they're there for sort of completion. Okay.